Good afternoon, class. We are looking at section 3.5, the chain rule. We have covered the derivatives and rates of change. The derivative as a function, basic differentiation formulas, the product and quotient rules. We're going to go over the chain rule, the synopsis of that, when y is f of g of x, the composite function. And we want to differentiate that. F is the shell function, the outer function. G is the inner function. Then we differentiate the outer function over the inner function times g prime of x. And this is in Leibniz notation. dy dx is dy du dx. So we are looking at things we've seen from before. Basic slope, rise over run. You take the derivative and becomes the slope of a tangent line, or the definition is dy dx, or the limit of delta y over delta x as delta x approaches 0. And these are the various formulas we have seen, basic differentiations, product rule, quotient rule, and now we are adding the chain rule. So let's make some sense out of this by starting with the composite function. When we have the function f of x and g of x, f of g by definition is f of g of x. The composed function f of g, the composition of f and g is defined as f of g of x. So when we write f o, that means f of g of x, and composite function. So we are given f of x equals x cubed, g of x equals 1 plus x squared, and we want to find f of g as well as g of f. So simply put, f of x, f of g means replace the x with g. So it becomes f of g, or 1 plus x squared, which means in the function f of x, we're going to replace the x with 1 plus x squared. And you don't have to raise it to the third power. If you want to go with g of f, by definition, it means g of f of x. That means g of x cubed. If you replace the x in the g of x with f function or x cubed, we get 1 plus x cubed to the second power. Since this we can simplify it pretty fast, we must, using the exponential rule known as the power rule, we get 1 plus x to the power of 6. And as you can see, f of g is not equal to g of f. In general, f of g and g of f are not equal in general. When would they be equal? Anybody knows when would f of g be equal to g of f? If we have two functions that are inverse of each other, f of f inverse equals f inverse of f equals x. If two functions are inverse functions, their composite function in any order becomes x, because they undo each other. All right. Why do we learn the chain rule? Well, how do we differentiate composite functions? Something like square root of 10x plus 5 or 10x squared minus 1 to the power of 50. The chain rule says if g is differentiable at x, and if f is differentiable at g of x, then the composite function f of g of x is differentiable at x. And the way it works, f is the shell function, the outer function. G is the inner function. So the derivative of f of g of x is the derivative of the outer function, f prime of g of x, times the derivative of the inner function, g prime of x. If we want to use the Leibniz notation, where y is a function of u is a function of x, then dy dx is dy du times du dx. If we assume those are basic fractions, you can see that we really can cancel them and we get dy dx. That's not the case, by the way. So what we are saying, if capital F represents f of g or f of g of x, then capital F prime of x, which is the derivative of that, is f prime of g of x times g prime of x. Here's the general power rule or the extended power rule. The derivative of x to the power of n, we know it to be n x to the power of n minus 1, known as the basic power rule. What if we have g of x to the power of n instead of x to the power of n? So we continue with the fact that we make n the coefficient, then we use instead of x g of x, and we make the exponent going down by 1, becomes n minus 1. And then by the chain rule, we tag along g prime of x. So one thing that may be helpful to see that, first of all, the general or extended power. Secondly, what is the derivative of x? It's 1, but we don't have to write it because it makes no difference. So the derivative of x, just actually clean this up, gives you 1. But what is the derivative of g of x? Now it makes a difference. You have to write. Now, a set of examples that will help us understand this better is what you see here. And I'm going to explain how we do that. That makes it easy to find the answer. For example, the first one is sine 2x, the second one is sine x squared, and the third one is sine squared x. Whenever you deal with these types of functions, you need to know what is the shell function, the outer function. So for a case like this, the way you do it, you just read sine and you pause. So y prime is cosine. So just pause. The derivative of sine is cosine. But you have to write the argument. This is the argument of sine. So you have to write the argument. Also, now by the chain rule, you need the derivative of this. Remember, if it were x, the derivative is 1. You don't have to write it. But it is not. It's a function of x. So times 2, and you put the 2 in front. Same thing happens here. Sine and pause. Y prime becomes cosine. You need to, for the argument, and then the derivative of x squared by the chain rule is 2x. You put the 2x in front. The last one, perhaps if we rewrite it, it helps. If I rewrite the last one as sine x to the second power, and now we realize we are dealing with the extended power rule, which means n, so we make 2 the coefficient, then we write the same thing, sine x to the power of 2 minus 1 over 1, so 2 sine x to the power of 1, and then g prime of x, the derivative of sine, which is cosine, 2 sine x cosine x. Some of you may know this is equal to sine 2x, but that's fine, we don't have to write that. So I hope you go over the 3 again and you can distinguish among those, because they really help us understand what's going on here as far as the chain rule is concerned. I want to look at this example 2 ways. So y is u to the power of 5, which makes it a function of u. u is 10x cubed plus 2, which makes it a function of x. And we can use this notation. Leibniz says dy dx is dy du dx. We can use that. We can also find their composite function and differentiate it accordingly. So let's look at both ways. Dy dx is dy du times du dx. So what is dy du? We look at this function. When we want to take the derivative of y with respect to u, it is simply 5 u to the power of 4. Very straightforward. What is du dx? That means differentiate this, which is simply 30, 10 times 3, 30x squared. Practically, we're done. We have to replace the u with 10x cubed plus 2. We're going to multiply the 5 by 30x squared and put it in front. 150x squared times 10x cubed plus 2 to the power of 4, and we're done. So we used the Leibniz's notation. If we want to find their composite function, f o g, then replace the u with 10x cubed plus 2. That gives us the composite function. 10x cubed plus 2 to the power of 5. And now we are going to use y prime is f of g quantity prime, or f prime of g of x times g prime of x. So in essence, we are using the extended power rule. N is 5, put it in front. Then write g of x just the way it is, whatever is inside the parentheses, to the power of 5 minus 1, which makes it 4, times g prime of x, the derivative of the inside is 30x squared. So 5 sits in front. We write the same thing to the power of 4. And now we need g prime of x, which is 30x squared, the derivative of the inside. And of course, we combine these two, we put them in front. 5 times 30x squared comes in front. And as you can see, it's exactly the same answer as we had it here. Two different methods, and we are fine. All right. Let's go to the next page. We want to differentiate 10x squared minus 1 to the power of 50. We can clearly use the extended power rule, which means I'm going to put number 50 in front. Then the same thing to the power of n minus 1, which makes it 49. And then the derivative of the inside is 20x. So quickly, if we were to write that, I could say, okay, I'm going to bring 50. So this is y prime in front. And I write the same thing inside the parentheses to the power of 50 minus 1. And I'm going to multiply by the derivative of 10x squared minus 1, which is 20x. And of course, I'm going to combine these two, put it in front. I get 1000x times 10x squared minus 1 to the power of 49. To differentiate this, we are going to use the algebraic technique and rewriting it as 10x plus 5 to the power of 1/2 first. Then we use the extended power rule. which means the exponent becomes the coefficient. You write whatever is inside the parentheses, and you raise it to the power of the same power minus 1. And then the derivative of the parentheses is simply 10. And of course, 10 and 1/2. Now this 10 and 1/2, they give you 5 over 10x plus 5 to the power of positive 1/2, which is a square root. And that's the final answer. To differentiate this, number 5 in front remains. In other words, you would say y prime is 5 and don't change that. So you're dealing with 3x minus 2 to the power of 4. So you have to bring the 4 down and you make it a coefficient. Then 3x minus 2 to the power of the same thing, 4 minus 1. And then the derivative of the parentheses 3x minus 2, this is g prime of x. So this is n. This is g of x to the power of n minus 1. This is g prime of x, the derivative of the inside. Now 5 times 4, 20 times 3, 60 comes in front. We want to differentiate e to the power of x, and we know the derivative is itself. But what happens if we have e to the power of kx? By the chain rule, we have to tag along it g prime. So the derivative is itself and then times the derivative of the exponent. Remember, in this case, the derivative of the exponent is 1. We don't have to write it. In this case, the derivative is k, so times k. In this case, the derivative of g of x is g prime times g prime, and we put it in front. So the way I'm going to approach this is very simple. I'm going to say y prime is itself y, because it's an exponential. And then I look at the exponent and say if it's x or t or theta, I'm done. But it's not. I need to differentiate 10x. I get 10. I put it in front. And I'm done. Number 10 should be written in the front. Same thing here. I want to differentiate this. So I'm going to write y prime is itself because it's an exponential function. And then I need g prime of x because the exponent is a function of a t. Then the derivative of t squared is 2t, and I'm going to put that in front again. When we look at this example, I highly recommend you take the first step and rewrite it as e to the power of 2t, although you can differentiate it the way it's given, but it's easier this way. Now y prime is itself times, we need the derivative of 2t, and we put the 2 in front, and we're done. So dealing with exponentials, when the base is e, but the exponent is a function of x or t. We're going to differentiate y equals 5x times 3x minus 2 to the power of 4. And first, I want to explain something about number 5, everybody. If 5 is involved, that means it's a large number, or if it's a fraction, or if it's a decimal, probably you want to put brackets here and differentiate it in that format, because that 5, any number that is will carry on. Because 5 is a fairly small number, you can say it's 5x and differentiate it as part of x. Eventually, it will be factored out. It must be factored out. So we are looking at this function, and this function. So this is f times g, which requires the product rule. Fg prime is f prime g plus g prime, if this is a shorthand notation. So I will quickly go over that. Therefore, the derivative of 5x, which is 5 times 3x minus 2 to the power of 4, plus the second piece, I use the extended power rule, 4 times 3x minus 2 cubed times 3, and now times the first piece, which is 5x. So this is a better way of seeing in the next line, but I want you to see that we are looking at, let me just write the top of it so you see, this is f prime g, this is g prime f. And this is the only calculus step we are done. With the calculus, we are going to continue with algebraic techniques to finish the job. So right here, 4 and 3 and 5x, their product is 60x. So we want to factor the two. We notice that 5 is in common. You can see it right here, or between 5 and 60. 3x minus 2 is in common. The exponent is 4 here. The exponent is 3 here, so we're going to go with the exponent 3. So the common factor of 5 times 3x minus 2 cubed must come out. This factoring is extremely important. So when I divide this one by this one, gives me 3x minus 2. When I divide this one by this one, this completely goes away. 60x divided by 5 gives me 12x. Okay, so again, this will give me 3x minus 2, but the second part, 12x. As you can see, 3 and 12, they add up to 15. So we have 15x. And that's the final answer. Over here, anytime the numerator is a number, we don't need to use the quotient rule. We bring everything up in this format. And as you can see, I can use the extended power rule. N is minus 4. Then 7x squared minus x to the power of minus 4 minus 1. And then times the derivative of the inside, 14x minus 1. So this is minus 4 minus 1. And this is really g prime of x, where this is g of x. So again, a quick recap to make sure we understand what happened here. Negative 4 becomes the coefficient. You write the same thing and you go down by one notch. So minus 4 minus 1 makes it negative 5. This is the derivative of this. And this will go down and give you positive exponent. Very straightforward class. We want to differentiate this, which means we are looking at a quotient rule to begin with. That's why I'm rewriting the quotient rule for you here, f over g prime, shorthand notation, f prime g minus g prime f over g squared. So I'm going to write, this is f, this is g, and I'm going to follow this. So I have a fraction bond, and f prime, the derivative of this one is 1 times the bottom. So f prime g, I want minus g prime f. What is the derivative of the bottom? I use the extended power rule. 4 times 2x minus 1 cubed times the derivative of the inside, which is 2, and then times g prime, which is x. This is g prime. And I just write this one, and I want to raise it to the second power, so 4 becomes 8. So if I want to write underneath, so this is f prime g minus g prime f, and the bottom is g squared. All right, as you can see, 2x minus 1 cubed is in common, right? 2x minus 1 is in common. This has exponent 4, this has exponent 3. We go with the smaller of the two. And when I divide this one by this one, I get 2x minus 1. When I divide this one by it, I have negative 4 and 2x left, which gives me negative 8x. This one cancels out this one and changes number 8 to 5. And these two add up to negative 6x. And we are done. All right. You want to differentiate this, which means we're going to change this to x squared plus 3 to the power of positive 1/2. You bring it up and it becomes negative 1/2. The reason we do that, because the numerator is a number, we don't have to do the quotient rule. So we can use the extended power rule step by step. N, now before I go to N, first I have this number 4, so I'm going to write it. I'm not going to change that. This is not going to go away. So y prime is 4, so that one is, now the rest of them, I'm going to look at this one, N, so minus 1/2. G of x to the power of n minus 1. I write this one to the power of minus 1. Minus 1/2 minus 1 becomes negative 3/2. And then I need g prime of x. What is the derivative of the inside? 2x. So again, I want to make sure that we understand that here, this is negative 1/2 minus 1. So we are going to multiply 4 and negative 1/2 and 2x. So 4 times negative 1/2 is negative 2 times 2x gives me negative 4x, and I put it in front. Again, I'm done with calculus here with the asterisk next to it. I'm just doing more algebraic techniques. Now negative 3/2 is the exponent. I can take it down and make it positive 3/2. And I'm done with that, but some of you may know that and may remember that this can be written as x squared plus 3 times the square root of that, and you don't have to make that transition just in case. Very straightforward. We want to differentiate y equals cosine 3t to the power of 4. And I'm going to start with the way I mentioned it at the beginning. Anytime you have sine, cosine, and things of that nature, you want to pause. So I'm going to read cosine and I'm going to pause. And that gives me y prime equals negative sine. Now, what is the argument of cosine? Argument, this is the terminology we use in trigonometry. Then I need the same thing. So cosine becomes negative sine, and you write the argument 3t to the power of 4. By the chain rule, I need the derivative of this piece. So I need the derivative of 3t to the power of 4, which is 12t cubed, and I'm going to put that in front, and I'm done. So anytime you deal with sine, cosine, so on and so forth, perhaps the best course of action is to pause after you mention cosine or sine. It makes it easier to see what is your shell function. What is it that you're differentiating? You're differentiating cosine, which gives you negative sine. And you have to keep the same argument. And then the argument, it is a function of x or t or theta. You differentiate it by the fact that you need g prime of x or g prime of t in this case. When we look at this one, we have to use the extended power rule first. So I put 5s in front. Then I write exactly the same thing. G of x is whatever you see here to the power of n minus 1. So I need to write the same thing to the power of 5 minus 1, which is 4. And then g prime of x says, differentiate inside the parentheses, which requires the quotient rule. The quotient rule. If this is f, this is g, you need from the top, the derivative is 2 times the bottom, x minus 8 minus g prime f minus the derivative of the bottom is 1 times the top minus 1 times 2x plus 3 over g squared. This is x minus 8. Just square it down here. And again, you're done with calculus. What is left is a matter of simplification. That's what we are going to do here. So this fraction in the numerator, I see 2x minus 16 minus 2x minus 3, and clearly these two cancel out, and we add up the two numbers to negative 19. Now, the next step, I write it for the sake of those who may not notice that we can combine these two. So we have this, we have this, we have this. We're not going to change it. This one, I'm going to change it to 2x plus 3 to the power of 4 over x minus 8 to the power of 4. And I'm going to write the last part. And so right away, we recognize the denominator becomes x minus 8 to the power of 4, and 2 add up to 6. Now everything goes at top, 5, negative 19, and that. The product of 5 and negative 19, remember, you can write this as 5 over 1. 5 and negative 19 is negative 95. We have this part, and the denominator, as I said, 4 and 2, they add up to 6, and we're done. All right, we want to differentiate this, and again, we are dealing with the exponential functions. So the very first thing I do in each case, I just write the function. So e to the power 5t. Since it's a function of t, I need the derivative of 5t, which is 5, and I put it in front. In this case, e to the power of tan x. I need the derivative of tangent, which is secant squared x, and we just write it the way it is, because if you put the secant squared in front, you gotta put a raised dot, because we want to make sure we understand that it's not xe if you put it in front. So it's e to the power of tan x, secant squared x. The last one, I want to make sure that you can see that this means 2/3 x, because when we see that, when we see the derivative is itself, and we need the derivative of the exponent, which is simply 2/3, and we put that in front, and we are done. What happens when the base is no longer e? We are familiar with the case when the base is e, but what happens when the base is not? We don't know it. Let's figure it out. So for example, if we generalize it to b to the power of x, how do we take care of the business? Well, first, let me remind you of what we learned in algebra. Ln of e to the power of x is x, e to the power of ln x is x, meaning logarithmic functions and exponential functions, they are inverse functions, they undo each other. As long as these two are the same, we can write them in this fashion. So we don't know how to differentiate this, but we know how to differentiate it if the base was e. So for example, here, if I want this to be b, this becomes e to the power of ln b. You see that? If I want it to be 3, then it's e to the power of ln 3. So we're going to stick with this for now. And we're going to change the b to e to the power of ln b. And by the power rule, these two get multiplied. So ln b is a number times x. And this we know how to differentiate according to this. The derivative of this is itself, right? And then times, this one was times k. Remember, ln b is like k, ln b is a number. So the same thing times k, which we are going to replace it with ln b. Now, since e to the power of ln b is b, so we're going to put that back. This part is the same as b. So we're going to put that in the format of b to the power of x ln b. So if I want to differentiate this, first I write, it's an exponential format, and it doesn't matter what the base is. First, I'm going to write it itself, 3 to the power of x, times, because the base is not e, times natural log of the base. This is by logarithmic properties, times ln 3, and we are done. I just rewrite. And we keep it in this format. If you put it in front, one may read as ln of 33 to the power of x. So keep it in this format. You can keep it with the raised out or without. But if I want to differentiate this now, in addition to what happened in the previous case, now this is a function of x, the exponent, which means we continue with the same concept here. We know how to differentiate this. We just write the answer and then multiply by g prime of x. So the same thing happens here times the derivative of 7x, or in general, g prime of x, or if we call it b to the power of f of x, then y prime is the same thing. ln b, because the base is not e, and f prime of x because the exponent is not x, it's a function of x. So how do we do that? First and foremost, we repeat it. Y prime is itself. Y because an exponential function. What is the base? Is it E? No. Then we need ln B. So we need ln2. Is this x? No, it's a function of x. Therefore, we need the derivative of that by this or that rule, which means I need 7. And now I'm going to rewrite it by putting 7 ln2 in front. This is normally the way we write it, but it is absolutely up to you. You want to be careful. You write this in a parenthesis or you put a raised dot so we don't think it's 22 here. Could somebody read this question, please? Anyone?
I can read it.
Please.
After T weeks, the number of people using a new rapid transit system was approximated by the formula n parenthesis t parenthesis equals ct to the square root of 2 plus 500t plus 8,000. At what rate was the use of the system changing with respect to time after 8 weeks?
Excellent. This is n of t. N is a function of t. And a couple of things I want you to notice. The moment you see rate, that means either instantaneous rate, which means differentiation, or average rate. But when you look at this one and it says after 8 weeks, that means instantaneous because it's 1 point in time. So look at that and make sure you realize why we need the derivative. So we need n prime of t. N prime of t is 12t plus 500. And we want it after 8 weeks, replace the t with 8. Twelve times 8, 96 plus 500 is 596. It's important to see that n prime means dn dt, changing n, the numbers, the number of people, over the change in time. That's how we get this unit, 596 people per week. What does it mean? It means on week 8, the number of people using the transit is increasing at a rate of 596 people per week. And why are we using increasing? Because this number is positive. If it's negative, we would use decreasing. Okay. Could somebody read this one, please? Okay. A bacterial colony is estimated to have a population of P of t equals 24t plus 10 over t squared plus 1 million t hours after the introduction of a toxin. What is the population after 1 hour? This is elementary algebra, plug in 1. 24 and 10 is 34. 1 squared, 1 and 1 is 2. And the answer is 17. Why is it 17 million? Because when they gave us the question, they gave us the population in millions. So 17 million bacteria. At what rate is the population changing 1 hour after the toxin is introduced? Again, we have the rate, which means either average or instantaneous. 1 hour, so 1 point in time, it means instantaneous, it means differentiation, and we have to use the quotient rule. So the top, so I want p prime of t, so the top is, that gives us 24 times t squared plus 1 minus the bottom gives us 2t times the top 24t plus 10 over the bottom squared. That is p prime of t. So let me write at top of it that we have f prime g minus g prime f over g squared. I'm going to clean it up and simplify it for you. Okay. So I need to clean up the top. And now this is 24t squared plus 24 minus 48 2 squared minus 20t. And these two, we can combine them into negative 24t squared, and we write the rest. Negative 24t squared minus 20t plus 24 over t squared plus 1 quantity squared. And now we want it after 1 hour. We're going to plug in. So we want p prime of 1. We plug in. So it becomes 1 squared is 1 times 24 minus 24 because we have a negative sign. Minus 20 plus 24. Clearly these two cancel each other. This is 1 squared, 1 plus 1 is 2, 2 squared is 4. So minus 20 over 4 is negative 5. But why is it negative 5 million bacteria? Again, the same thing as happened here. Minus 5 bacteria per hour. Remember, p prime of t was dp dt in Leibniz's notation. So the change in population over the change in time. So minus 5 million bacteria per hour. Now, how do we explain this? The population is decreasing, and that's the key. Why do we write decreasing? Because we have a negative sign. We don't have to write it with negative here. The population is decreasing. This gives us the answer at the rate. See, this 5, we have to keep it as positive because decreasing makes it negative. At the rate of 5 million bacteria per hour, 1 hour after the toxin is introduced. Observations show that the length L in millimeters from nose to tail of a Siberian tiger can be estimated by the function L equals 0.25 W to the power of 2.6, where W is the weight of the tiger in kilograms. Furthermore, a young tiger's weight can be estimated in terms of its age T in days by the function W equals 3 plus 0.21 T. How long is a tiger when it's 100 days old? This is elementary algebra. You replace the T with 100, and that gives you the weight first. And 0.21 times 100 is 21. 21 and 3 is 24 kilograms. But we want the length, so plug it into this, because remember, L is a function of W, W is a function of T. So you could write L as a function of T, by replacing the W and in one shot come up with the answer, or just you calculated the weight, now you plug it in here, and at this point, you really have to use a calculator. So 0.25 times the number we just got, 24 to the power of 2.6, using calculator gives us this. And I want to remind you that uh, 1 meter is 100 centimeters. In it is 1,000 millimeters. So this is close to 1 meter, and 1 meter is about 1 yard, and 1 yard is about 3 feet. At what rate is the length increasing when it is 100 days old? Again, we are looking at rate, which means either instantaneous, which means differentiation, or average, because there is one point in time. It means instantaneous, it means differentiate, it means we want dl dt. Now, there are two different ways of doing it, as it was the case here. And I'm going to go with the Leibniz's notation for now. dy dx is dy du du dx. So in this case, I want dl dt. I'm going to put the dl here and dt at the end. And then the intermediate variable, L, is a function of W. See, W is 3 plus 0.21 t. So the intermediate variable over here was U. Over here is W. So we have dW in both of these places. And I wrote it in this fashion so you can easily figure out what you have to use here. So what is dLdW? Take a look at this one. This is 0.25 remains times 2.6 becomes a coefficient, W to the power of 2.6 minus 1, or 1.6. So this is dW, dLdW. What about dW dt? Take a look. dW dt is simply 0.21. dW dt is just 0.21 class. If I want to put them all together, I'm going to multiply this number by this number by this number and put it in front. If we were finding the derivative function in general, we must replace the W with 3 plus 0.21 t to make it a function of t. But because we are asked to come up with the rate when it's 100 days old, we know that W, the weight when it is 100 days old, is 24. So replace the W with 24. So 0.1365 times 24 to the power of 1.6, using a calculator, we come up with 22.0532. And you want to use as many decimals as you can, unless they ask you specifically how many. And this is dl, change in length, millimeters, over dt, change in time, which is in days, so millimeters per day. And we are done. But I want to show you a second method. And by that, I mean, I have to find L as a function of a t, which means I'm going to replace the W with this expression 3 plus 0.21 t. Now, this is a function of t. And for part A, all I have to do, replace the t with 100. And if I go through the process, I get exactly the same answer as I got here. But I use the composite function. I found the composite function. Now I want to differentiate this one, dl dt, or L prime of t. So 0.25, you keep it, and then you bring the 2.6 in front, the same thing to the power of 1.6, because you're subtracting 1, and times the derivative of the inside by the chain rule, which is 0.21. So again, 0.25 you keep, 2.6 you put it in front, the same parentheses, you write it to the power of 2.6 minus 1, which makes it 1.6. The derivative of the inside, 0.21. You multiply this one, and this one. We had already done that in the previous case, and so it's 1365, and then the parentheses. And now, if I replace the t with 100, I get exactly this answer that I got here. The difference is this is a composite function. I found the composite function, and the composite function wasn't difficult to find. So I did it two different ways, using Leibniz's notation, using the composite function. In some instances, it's not easy to find the composite function. That's why you really want to know both. The amount of glass recycled in a community is given as G of P equals the square root of 0.5 P squared plus 7 tons, where P is the population in thousands. It is estimated that 10 years from now, the population of the community will be P of T equals 4.4 plus 0.1 T squared thousand. How many tons of glasses are expected to be recycled 4 years from now? Well, again, this part is elementary algebra, and that means you want to plug in T equals 4 first to find the population. 4 squared is 16. 16 times 0.1 is 1.6, and 4.4. They add up to 6, and it's thousands, okay, because of this 1,000 people, 6,000 people. And now that we have this, we plug it in here to find the amount, because we are looking for how many tons of glasses. So when you plug in 6 here, it gives you tons of glasses. So when we plug in, what do we get? Let me quickly show you. So this is 36. Half of that is 18 plus 7. That makes it 25. And square root of 25 is 5. So the answer is 5 tons of glass. So elementary algebra. What is the next part? The next part says find the rate at which the amount of glass recycled is changing with respect to time 4 years from now. Again, rate, it could be instantaneous, or it could be the average. Because we have only one point in time, it is instantaneous. So we want to find the rate at which the amount of glass, that means dg over the time dt. We are looking for dg dt. So I'm going to use the Leibniz's notation, and I'm going to write dg over something times something over dt, because I want to help you figure out what goes in between by looking at g being a function of a p, and then p is a function of t, which means the intermediate variable is p. So I need dg dp and then dp dt. I'm showing you how to find that in general. So to differentiate this, first I'm going to rewrite this as 0.5 p squared plus 7 to the power of 1/2. Okay, I want to quickly show you how it's done. So I'm interested in dg dp, okay? So dg dp, you have a 1/2 times the parentheses, whatever it is, 0.5 p squared plus 7 to the power of 1/2, and I'm going to subtract 1. And then I need to tag along the derivative of the inside. The derivative of the inside is 0.5 times p squared gives me 2p. So this 0.5 times 2p is this. And 1/2 minus 1 is negative 1/2. 0.5 times 2p gives me p. This is dg dp. Now what is dp dt? Let's go to the function here, 4.4 plus 0.1 t squared. So the derivative, when you take it with respect to t, becomes 0.1 times 2t, which makes it 0.2t. So this one is 0.1 times 2t. Now, we don't have to simplify because we just want to evaluate it. Of course, we can simplify it, make it a function of t, all of the above. Since we want to find the rate 4 years from now, we are going to replace the t with 4 and p with 6, which we found before. So replace the p here, this one and this one with 6, and t, only this one, with 4. Let's replace. So what happens is that I showed you this one is 5. So this one, when you take it down, remember what this is. This one is 25. So this one is 25 to the power of negative 1/2, which means 1 over 25 to the power of positive 1/2, or 1 over square root of 25, or 1 over 5. So we have 1/2 times 1/5 times 6 times 0.8. Okay, now this one drops this one. So you have 1 times 3 times 0.8 over 5, which becomes 0.48 tons of glass over years, because we are looking at dg dt, the change in the amount of glass over the change in the number of years. So tons of glass over year. That's how you come up with the units, and that is extremely important to know how to arrive at units.